Hello everybody, my name is Kai-Uwe. I'm excited that you have decided to join those videos about form finding with the force identity method. These are records of the presentations of the workshop I gave last year in Zurich on the occasion of the annual conference of IASS, the International Association of Shell and Spatial Structures. The course is about to tell you the background, the mechanical background of the force density method, a very famous method invented by Klaus LInkwitz and Hans-Jörg Schek on the occasion of the Olympia station, the Olympic roof in Munich, 1972. The idea is just to show you how this technique, which was invented within a very short time at the end of 1969, to show you how this method is nevertheless very nicely embedded into basics of continuum mechanics. Insofar that might be insights which might be new to you, at least they are very interesting, and we will end up, as we will see at the end, in very effective and efficient algorithms to implement the force density method. What I show you here, as I said, is a revised version of that workshop. And it's structured like you see here. So we start actually now with the introduction. Then we have other videos numbered by 1 to 4, which are about work and energy theorems, the principle of virtual work. That means we will just briefly repeat those basics which you may perhaps have been heard about in your studies. Video number 2 is about nonlinear strain and strain measures, stress measures along this direction, and last but not least you will see how these stress measures, which are very well known from basic mechanics, are nicely identified as force densities. And third, we just go into the general method in total. Another force density method. We go into what is called the linear method and the nonlinear method, just as they have been defined earlier already by Hans-Jörg Schek. And last but not least, you will also see that we come into some non-conservative issues if we go into loads like self-weight and snow. And last but not least, we will conclude our workshop with some numerical aspects which just appear when just consistently implementing this technique as a nonlinear numerical method at the state of the art. Also, I should not forget to advertise our educational software Stiff3D, which is accomplishing this workshop. It's based on Microsoft Excel, desktop version, and Visual Basic for application. And we're treating all the issues which are the content of this workshop: linear, nonlinear force density method, constraints on member length, projected length, node position, prescribed member forces with the updated reference strategy, self-weight and snow on cables, consistently considering the change of length during the iterations of the form finding, determining minimal path networks, applying us, and being able to do a completely nonlinear analysis with prescribed member forces, if that is possible, of course. We have an interactive GUI and sophisticated design tools so that you are able to interactively set even most complex problems. Nevertheless, we should consider that it is a educational software. That means it's not made for large applications. That means with very many degrees of freedom. It's just designed to be on a smaller basis. But you will see it if we just look at examples throughout the workshop. If you like and you are interested to receive Stiff3D, just refer to the chair's homepage or contact me directly through email. There's a list of accomplishing videos you may find on YouTube. Here are the links. 12 tutorials for Stiff3D in English language, where we just go through all the important issues if you would like to set up form finding problems with Stiff. Yeah, that's about it. I'm happy that you're here. I'm looking forward to a very exciting workshop. Thanks. Let's start with a brief look at the history of the force density method and as it has evolved. As you may know, and as I said, the force density method was invented on the occasion of the Olympic Games in Munich 1972, and the design and the construction of the Olympic roof. You see it here, the actual status of this roof, with the stadium, the gymnasium and the swimming hall, and some connecting roofs in between. On the left you see the design, the sketch of the architects when they just joined the competition, and that was the basis when they just won this competition. And you see, the original idea was just to cover these three locations, stadium, gymnasium and the swimming hall, just by one unique roof which was covering everything. Comparing to what you see on the right, that was the important change done by the engineers to divide this large roof into three parts, as I just have shown you. The Olympic roof could not be thought at all without knowing of the German pavilion on the Expo 1967, just a few years earlier in Montreal. And if we just compare these two, you see, indeed, it's the same construction. Because in those days there was no textile material available which was able just to span these large spans. In Montreal already, although it was much smaller than Munich, you don't see it on this figure. So the people just came up with just taking a cable nets instead. Cable nets made of steel. We have the edge cables, we have the posts, the columns, where the edge cables just carry the load to, and the surface covering smaller cables here just running lateral to each other. These small cables here, and what you see here, these black thick lines, this is just the insulation between these large pads of the cladding made here of translucent material made of plastic. It was clear, it must be a cable net, and that's how it came at the very end to the force density method, in particular for the shape and form finding of cable nets. Let's take a brief look at the people behind the scene, and indeed that was a group of very strong characters. From left to right you see here the architects, the competition-winning group of architects under the lead of Günter Benisch, together with Heinz Islerswim here on the right as the advisor with respect to structural aspects. In the center you see the members of the Planungsgruppe Dach, the roof planning group, which was just the implementation of the experts from engineering who were just expected to be able to make the whole thing running. Here you see Fritz Leonhardt. He joined the group in the meantime, as well as Frei Otto, as architect and the pioneer of lightweight structures and membrane structures. They too, Frei Otto and Fritz Leonhardt, had also been responsible for the roof in Montreal. In the very center you see the young Jörg Schek. He was 33, 34 years old at the time, and he was the chief engineer. He was a member of the bureau of Fritz Leonhardt, also together with Rudolf Bergermann and Knut Gabriel. And as you may know, Rudolf Bergermann and Jörg Schek later founded their own bureau, Schleich, Bergermann and Partner, very famous in the meantime as well. Here we see also Fritz Auer. He was a member of the architect group who are just representing those in the Planungsgruppe Dach. To the most right you see two pairs of people, the geodesists Klaus Linkwitz and Hans-Jörg Schek, responsible for the determination of the cutting patterns, and insofar that was a very crucial part of the whole business, simply because without highly exact determination of the cutting length it would not be possible at all to really erect the mesh. I will come to these two guys later on the next slide in more detail. Klaus Linkwitz, he was also, together with Frei Otto and Fritz Leonhardt, member of the group from Montreal, and these three just brought in the specific expertise for Montreal to make Munich possible. Here at the bottom, under the title Computational Mechanics, you see John Argyris and his co-worker Dieter Scharpf just was not able to find a photograph of him. John Argyris and Dieter Scharpf, he just stepped in, because it just appeared that the size of Munich was so much larger than the size of Montreal that indeed modern computational tools appear to be necessary to do the structural analysis. In particular, they are responsible for the structural analysis and the form finding for the gymnasium. Now, to concentrate on Klaus LInkwitz and Hans-Jörg Schek, as I said, their duty in particular was to develop the cutting length of these cables and to produce the working drawings. And they did that with their standard tools from geodesy, photogrammetric determination of the geometry from physical models, and applying adjustment analysis to receive the best accuracy possible. And in the course of the project, they just finally developed the force density method for numerical form finding. The reason why we see just in a second. Though that's a map, a drawing of these cutting patterns for these cables. And as I said, that was the goal, their duty, to exactly develop and produce those. Until Munich, it was state of the art, without any expensive or just high fidelity analysis. The complete form finding and the analysis was done in physical models. On the left, you see the model for the tent in Montreal, and on the right, you may easily identify, indeed, that's the tent across the stadium of Munich. What you can't see on these two photographs is the scale of this model, and that makes a big difference. It's approximately the same basic frame where these two tents, these two roofs has been arranged to. And indeed, the scale of the Munich model here was very, very small. And that was the reason that precise measurements, even with the best photogrammetry, was impossible to do that in the necessary precision. Moreover, because of the large forces, even in the model, the basic frame was deformed, so the measurement was not good enough at all to create the cutting pattern from that. And that came to the point that Klaus LInkwitz and Hans-Jörg Schek had more or less been forced to develop numerical tools to come up with good data and information about the details of the geometry to be able to do the cutting pattern. And that was the invention, the basis of the invention of the force density method. That was in the about Christmas 1969, a few years before the Olympic Games should have been started. And there you see under which pressure this technique was developed. What you see here is one of the first papers which appeared in German, and it's very impressive, at least for me, just to identify all these terms which we are used to apply for nonlinear analysis of structural analysis nowadays. Here you see these equations to determine the geometry from elastic deformations with the geometry in form as a function of the elastic internal forces, the external forces. Here this expression, that's the elastic stiffness matrix. That is the geometric stiffness matrix, what you need for nonlinear analysis. And you see here roughly sketched the updates procedure of the Newton-Raphson iteration, what they have applied. And you see also the notation is pretty much different of what we use nowadays and what civil engineers had been using also in those days, which made it difficult to read what geodesists had been writing and how they interpreted that. Finally, that was the result of the first applications of the force density method. You see here the computer graph here, the computer drawing of the form find roof. In particular, that's this part of this connection roof between the gymnasium here to the left and the stadium here to the right, at the north entrance of the Olympic Park. And Klaus LInkwitz, he was very proud of this little piece, because he said, at the end, when we came to the end, we really knew about what to do and how to do it, and to receive the best results of what we could. You see him as he has a little field trip to the north entrance. And he said, that's the masterpiece of Frei Otto. He just was referring to Frei Otto. A shape as close as possible to minimal surfaces. But we can also say it was really the masterpiece of all the guys, all the people who just have been part of the group. And here we come to the first paper in English, written by Hans-Jörg Schek, who became very famous in the meantime, from 1973. It appeared in 1974, as you may see, in Computer Methods in Applied Mechanics and Engineering. And in this paper you can see everything what is of importance. You see the definition of what is the force density. It's the ratio of the cable force S over the length of the link. You see a little mesh consisting of nodes and branches. And here we have also to adapt the understanding of geodesists. Instead of seeing a cable net, first of all, they see a mesh of orientations and observations, just as typically geodetic nets are just defined. And S is the force with one of these links, for instance here link 3 or branch 3, and L sub J is just the length of this branch. The length of member, I say member, and the force in member and the ratio of these. And as geodesists are used to, they typically formulate everything in vectors and matrices. As you see, we can arrange a vector of member forces, where we just collect all the forces of members 1 to R, as you may see. We can also do that for the force densities, collecting these in a vector, but also it was defined by Klaus and Hans-Jörg to define a square matrix Q where these individual force densities are just aligned at the diagonal of this matrix. Straightforward, the matrix L of the member lengths is a diagonal square matrix where just the individual lengths from member 1 to member R just are arranged in this square matrix. With these definitions of the matrix of L and the vector of S, we can also define or determine all the force densities Q arranged in this vector simply by the multiplication of the inverse of the matrix L, which means that we just take the inverse of all the individual lengths along the diagonal and multiply that with the vector of the cable forces. And straightforward, everything else regarding the force density method is consequently and consistently just arranged in vectors and matrices and products of these. Next step is just to introduce what is called the branch node matrix Z, where we just see the relations between the nodes and the branches as they are just connected. Now you see member 1. Or branch 1 is referring to node 1, and node 6 is saying it's from 2 or from 2. The minus is just defining the from, and the 1 is the 2 node. And if we just compare, if you like, you will see here the topology and the relations between nodes and branches just collected in this matrix C. It's nothing else than an ordering and the statement of the relations between nodes and branches. And then they just wrote the 3 equations of equilibrium in X, Y, and Z direction at every of these nodes. And you see here this matrix of the force densities as defined before, and here this branch node matrix eventually transpose. And these 3 lines is the complete system of equation expressing not more than the equilibrium at the nodes, together eventually with some external loads in X, Y, and Z direction. Little bit simplifying what you see to the left by introducing these matrices D and DF as the product of those guys, where F is referring to the fixed node, that means the supported nodes, in this case 6, 7, 8, and 9. Also we see a respective part of this French node matrix here to the right, that is CF, and we can solve these equations for the geometry in terms of the coordinates of all of the nodes in x, y, and z direction. And you see what we have to do is just taking the inverse of the matrix D as abbreviated here and multiplying that with the load. And if you take that to the right hand side, the support forces. That's it. And it just appears that this is a system of linear equations where we can solve for the geometry in equilibrium in one simple analysis. And that is the wonderful, the very impressive property of the force density method, that at one linear step, very robust operation, the geometry in equilibrium can be determined, and even more by back substitution also the member forces, the cable forces in every cable can be determined simply by inverting again this relation that we started with the definition of the force densities, just multiplying the defined force density with the actual lengths collected in this matrix L, which can now after solution be determined applying Pythagoras from the deformed geometry. Yeah, that's it. That's in rough terms, in very short terms, the complete force density method as it was defined. The problem which arrived was that because of this little bit fancy formulation and the use of matrices and vectors was puzzling many people, in particular from architecture, and the method was blamed as a complicated vector matrix method. But as we see, it's not about the matrices and the vectors. It's simply a matter of formulation, the collecting of the data, using vectors and matrices. The very kernel of the force density method are these three sets of equations, just stating the equilibrium between the internal forces, hidden here in the force densities, and the external forces just applied to the structure. That's all. So force density method is nothing else than playing with equilibrium. And that means that it is part of mechanics at this point. It's part of mechanics, and as I said already, the goal of this workshop is just to explore these relations between mechanics and the idea of force densities, and eventually also making use of vectors and matrices. Looking more in detail in this matrix D, it may look like that at the very end. You see it's a matrix where these force densities of these individual branches are just collected. On the main diagonal they seem to be just added, and if all of them are positive for cable with tensile cable forces, then you see basically a matrix with a positive main diagonal, and on the off diagonals you see eventually negative values, depending again on the equilibrium of the structure. As we go further, maybe you have heard already also of the term stiffness matrix. We will identify the stiffness matrix which we are used with in structural analysis, indeed identical to this Gaussian transformation matrix as it was called by Hans-Jörg Schek in his paper. And again, that is a little indicator how close the force density method is embedded in standard mechanics. If you go further in the paper of Hans-Jörg Schek, you will find this flow diagram which brings everything together. So these first boxes here are just representing the standard linear force density method as just explained. And down there you see further outer loops, let's say, with respect to the implementation in those days. And you see one box just referring to additional constraints. Think of prescribed lengths of cables, things like that. And it just appears that all of these constraints we can think of, which makes sense, practical sense, are nonlinear. And at this end, the force density method becomes nonlinear, simply because of adding constraints. And that is the entry point into what is called the nonlinear force density method. I think It's not really something special. It's simply the question of considering constraints, and then we have to accept that everything becomes nonlinear. We will also look into that in the workshop. And that's exactly the subject of the workshop. We try to introduce, I don't try even, I do it. We will introduce an alternative approach which is completely consistent with continuum mechanics. And along this line, we can really identify very interesting insights in the force density method. And you will also see how easily the techniques, what we have nowadays, are consistently extending the force density method to a very mighty technology. And that's what we will do. Don't be afraid. We will look into the mechanical basics of cables, and we'll end at the identification of the equivalence of the forces in the member in a special term, which is called Piola-Kirchhoff force of second kind. The equivalence of that with the force density as it was just defined. And that is a very important outcome of that, because that makes us able to easily extend the ideas of force density for form finding, everything from LInkwitz and Schek, to membranes, 2D structures, membranes with a two-dimensional state of stresses, where again we apply the principle of virtual work, the first variation, and instead of using force densities, we use now the Piola-Kirchhoff stress tensor with normal stresses and shear stresses, if you like, to find surfaces and the prescribed stresses. And if we take the identity tensor here for the stress tensor, we can easily find also minimal surfaces. Consistently, completely consistently, and completely equivalent to everything what we can find in cables. And we can straightforward easily add constraints. So we add to the energy term those constraints G, multiplied each of them with the Lagrange multiplier, and just solve again the first variations, the first derivatives of this functional to find the solutions. Again, we realize that constraints are nonlinear, and we come by that straightforward and easily from linear force density method into the nonlinear state, as it was already discovered by Hans-Jörg Schek. And there we come to the nonlinear equations, and we are now able to apply the standard techniques which have been evolved over the last decades. Iterative solution techniques, Newton reference, sequential quadratic programming, SQP, line search, the standard tool set which is available nowadays for nonlinear problems. And another thing is adding stabilization term by the square of the constraints used for line search and for the channel stabilization of this expression, which might be necessary and is indeed very helpful if we have very nonlinear problems, but we will see that. So that is the status of the art, completely embedded into continuum mechanics and completely just treated by the state of the art of numerical techniques. I would close this little introduction by a little outlook, just to show you what really can be done by applying these ideas through this Piola-Kirchhoff stresses to membrane and surface problems. Here you see on the left-hand side the application to a minimal surface, Costa's minimal surface, very well known from the literature. And as we see, we started now, so we have a local minimum, but we go further to a global minimum, the minimal surface of this, let's say, structure between these given boundaries, the circle at the top, here's the circle at the belly, let's say, and the circle at the bottom. On the right-hand side, you'll see a little application to a student project some years ago, where the students have been developed a very small tent, as you see, close to a minimal surface along these procedures. And what you see here, that's the initial geometry, the starting geometry with prescribed support positions here at the top of these posts, or there's a post here also at the back. and a cable, support cable, let's say, just pulling the structure to the bottom. And what you see is here just the final element mesh of the surface with little triangles, where we just prescribe the Euler-Kirchhoff stresses in a two-dimensional state of stresses. And if we just start the analysis, you see already the first linear step. Again, a linear step, the generalized force density method. We are very close to the final solution, which we will approach here in further steps. And after 7 steps, we approach the solution. Now this procedure for the iteration towards minimal surfaces, that's what we call the updated reference strategy, which has some reason why we call that, and that also I will explain you in this workshop. And that's, let's say, the latest status of our developments at the chair, where we just embed all these ideas completely into computer-aided design, directly connected with fine element analysis and the cutting pattern analysis, just by developing the stub curved surfaces into the cutting pattern plane. That's the state of the art, at least at our chair. And I would like to close this little introduction by again giving my respect to the inventors of the force density method, Klaus, LInkwitz and Hans-Jörg Schek. The force density method, you can really say it's an ingenious method created under the great pressure of the design of the Olympic roof, consistently grounded on mechanic principles, as we know in the meantime. Together with the state-of-the-art of numerics, it's ideal for any problem of form finding of surfaces, membranes and cable nets. Yeah, and that's again the workshop layout. We have done the introduction now, and I'm looking forward that you also join the presentations which are remaining, and the next one will be a little recall of work and energy theorems and the principle of virtual work, just to get closer to the understanding of the force density as really consistent part of continuum mechanics. Thank you again.